Okay, so let's dive into one of the biggest puzzles for self-driving cars. How do they build a perfect map of the world around them? Not in days or hours, but, instantly. Today, we're breaking down MapTRv2, an AI that's learning to do exactly that. All right, I want you to put yourself in this car for a second. It is pouring rain, you can barely see a thing, and the lane markings are practically invisible. For a person, that's stressful. For a self-driving car, getting it right is absolutely mission critical. So how on earth does it navigate with superhuman precision? Well, the secret isn't just about having better cameras, it's about having a smarter brain that can build its own map, right here, right now. So here's our game plan for this explainer. First, we'll get into why these perfect maps are such a headache to begin with. Then we'll look at the first clunky attempts to solve the problem. After that, we get to the big aha moment, see how that idea got refined into MapTRv2, and finally check out the absolutely incredible results. To kick things off, you have to understand that pretty much every self-driving car depends on something called a high-definition or HD map. Seriously, without one, the car is basically flying blind to the rules and the layout of the road. Now look, this is not your phone's GPS, okay? An HD map is this incredibly detailed, machine-readable blueprint of the road. It doesn't use pixels like a photo, it uses vectors, these clean, mathematical lines and points to spell out exactly where every single lane divider, every crosswalk, and every curb is located. It is the absolute bedrock for planning a safe route. So the old school way of making these maps was totally offline. You'd have these special mapping cars driving around for weeks on end. The whole process was wildly expensive. The maps were stale the minute a new construction zone popped up. And worst of all, they could actually be slightly misaligned with what the car's sensors were seeing in the real world. The solution? Online maps. Maps that are generated in real time by the car itself. Of course, building a map in real time is, as you can imagine, fantastically difficult. The first tries were a big step, for sure, but they were still pretty clumsy. They were slow, and they just couldn't produce the clean, crisp vector maps that a car's brain actually needs to navigate. A lot of those early models created maps that were kind of like a blurry, pixelated image, what's called a rasterized map. You can't just feed that to the car's planning system. It needed all these extra, slow, complicated steps to turn it into something useful. Other models tried to draw the lines point by point, like a really slow game of connect the dots. Not only was it sluggish, but it meant one tiny error at the beginning could cascade into a massive mistake by the end. And this is where the story gets really, really interesting. The researchers behind the original MapTR had this fundamental insight, a real breakthrough, that just completely changed how you could teach a machine to understand the road. Let's just boil the problem down to its simplest form. How do you teach an AI what a lane line even is? I mean, does it start at one end and go to the other? Does it matter which point you use as the starting point for drawing it? See, before this, the models were forced to learn one single, specific order for the points that make up a line. And this just created a ton of confusion for the AI while it was training. Why should drawing a line from point A to point B be right, but drawing it from B to A be wrong, if they both represent the exact same line on the road? It doesn't make sense. And this right here perfectly illustrates the breakthrough. A lane line isn't a strict ordered sequence. It's a set of points. The image shows that for a simple line, there are at least two perfectly valid ways to order the points. For something more complex, like a crosswalk, there are way more. The AI needed to understand that all of these are correct. They all represent the same shape. So this genius idea has a name: permutation equivalent modeling. It's really just a clever way of telling the model, hey, the shape is defined by the collection of points, and any valid order, or permutation, is equally good. This totally removes that old ambiguity and makes the AI's learning process way more stable and way more efficient. So that core idea was the foundation for the first MapTR, but it wasn't perfect. The team quickly figured out where it could be improved, and that's what led to MapTR version 2. The first MapTR had a few key weaknesses. For one, sometimes direction does matter. Think of the center line on a one-way street. The model struggled with that. Second, the math behind it was a total memory hog, which made it really hard to scale the model up. And finally, it just took forever to train. MapTRv2 came in and fixed all of this with 3 key innovations. It became semantic aware, which is a fancy way of saying it could finally understand that for things like center lines, direction is crucial. It used a brand new, super efficient method called decoupled self-attention that just slashed computational costs.
And it used a much smarter training plan to learn way, way faster.
Let's just hang on that efficiency gain for a second. This new attention mechanism just gutted the memory and computation needs. So what does that actually mean? It means the researchers could suddenly use more power to find more map elements and describe them with even more points, all while using less horsepower. It basically unlocked a whole new level of performance.
So we've gone through the problem, the big idea, and all the refinements. Now we get to the best part, seeing what MapTRv2 can actually do. And let me tell you, the results are, well, they're pretty stunning. And I'm not being dramatic here. The performance jump from the old methods to MapTRv2 isn't just a little step forward. It is a massive leap that completely redefines what's possible for online mapping. Take a look at this chart. This is the classic trade-off, speed versus accuracy. Everyone wants to be in that top right corner, super fast and super accurate. And who's sitting up there all by itself in the winner's circle? MapTRv2. It's not a trade-off anymore. It's just better. So how much faster are we talking about? An incredible 15 times faster than the previous best camera-based method. That isn't just a small improvement, that's a whole generational leap in performance. And all that speed translates to 33.7 frames per second. Now, just for context, 30 frames per second is what we consider real time. So what this tells us is that MapTRv2 isn't just a cool lab experiment, it is fast enough to be put in a real car, building its map of the world as it drives. And right here, you can see the magic happen. On the left, that's the raw, messy, complex view from the camera. And on the right, that is the clean, structured, perfect vector map that MapTRv2 spits out in a fraction of a second. This is what the car's brain gets to see. You know, you don't even have to take my word for it. The authors of the paper sum it up perfectly. They state that MapTRv2, and I'm quoting here, outperforms all the state-of-the-art methods by a large margin in terms of convergence, accuracy, and speed. In other words, it learns faster, it's more accurate, and it runs faster than anything that ever came before it. So this all brings us to one final big thought. We've just seen a technology that has, for all intents and purposes, solved the problem of real-time map creation. That's a huge piece of the autonomous puzzle put into place. Which really makes you wonder, what's the next major hurdle we have to clear on the road to a truly driverless world?